Let's dig into solving logarithmic equations. I have 8 questions, but this first one is a little bit unusual. It's the only one out of the set that has a logarithm in each term. So we have 2 times the logarithm of 3 to the base 2 minus the logarithm of x to the base 2, and we're told that's equal to the logarithm of 45 to the base 2. Regardless, first thing I'm going to do is ensure that I have one term on the left-hand side of the equation and one term on the right-hand side. This means using the properties of logarithms to rewrite this multiple and difference of logs as the logarithm of a single quantity. Let's get started with that. That means we'll take the multiple of 2 and turn it into a power as our first step. So we now have the logarithm of 3 squared to the base 2 minus the logarithm of x to the base 2, and that's equal to the logarithm of 45 to the base 2. I should point out that the reason that I can use the properties of logarithms here to condense this difference of logarithms is because all logarithms are to the base 2. If your bases are different, you will first have to change the bases so that they match. In any case, I'm going to do 2 steps in one in this next one here. I can evaluate 3 to the power of 2, 3 squared is 9, and I'll also convert this difference of logs into the logarithm of a single quantity. So we have the logarithm, base 2, of 3 squared or 9 divided by x, and that's equal to the logarithm of 45 to the base 2. So here's where this question is a little bit unusual. Because I have a logarithm of both sides, in other words, the logarithm of 9 over x to the base 2 is equal to the logarithm of 45 to the base 2, it's logical that the quantities I'm taking the logarithms of must also be equal. So here we find that 9 over x is equal to 45. To solve for x, we'll multiply both sides by x first to remove it from the denominator. That gives us 9 is equal to 45x. And finally, dividing both sides by 45 gives us our final answer. We find that x is equal to 1 over 5. Although this next question has lns, not directly written as logarithms, it's more representative of most of these logarithmic equations. That's because we have logarithms only on one side of the equation, and these are equal to a value. If it helps you as you're starting to get comfortable with ln to write ln as the logarithm to the base e, that's absolutely fine. You could write the ln of x as the logarithm of x to the base e, and the second term as the logarithm of 1/3 to the base e. These are equal to 1. Again, I'll use the properties of logarithms to write this difference of logarithms on the left-hand side as the logarithm of a single quantity. So here we're subtracting the logarithm of 1/3 from the logarithm of x, which means that we'll end up with x in the numerator and 1/3 in the denominator. That's a complex fraction, so let's rewrite that. X divided by 1/3 can also be written as x divided by 1/3 using the division symbol. We know that we can't actually divide fractions this way except by rewriting them as multiplication of the reciprocal. So we get x times 3, or 3x. So x divided by 1/3 is equivalent to 3x. So we have the logarithm of 3x to the base e. Or if you prefer, the ln of 3x is equal to 1. For every situation where I have a single logarithm on the left side equal to a quantity on the right-hand side, my next step will be to write this logarithmic expression in exponential form. I think of this as unwinding the expression, or reading the logarithm. This tells us that e raised to the power of 1 gives us 3x. E raised to the power of 1 is equal to 3x. Of course, we can only do this rewriting once we have the logarithm of a single quantity on the left-hand side. And in this case, we find that once we've rewritten the logarithmic expression in exponential form, we've practically solved it. The only thing we need to do is isolate x, and we do that by dividing both sides by 3. So we find that x is equal to e divided by 3, which we can leave as e over 3 to give the exact answer, or if you prefer, you can evaluate that to 0.906. Let's try some additional questions. There will always be several ways that you can approach a logarithmic problem. There are two ways I can imagine starting this first one. 2 times the logarithm of 2x minus 1 equals 1. One way I can do this is to use the properties of logarithms and take this multiple of logs and turn it into a power. So I could rewrite this as the logarithm of 2x minus 1 squared, still to the base 10, is equal to 1. Or because I have an equation, I can instead choose to divide both sides by 2. This cancels the 2 from the left-hand side, and we find that the logarithm of 2x minus 1 is equal to 1/2. Let's try it this way. I like this expression because we already have the logarithm of a single quantity on the left-hand side, and that's equal to a number on the right. So our next step is to rewrite this in exponential form. Remember that the logarithm is to the base 10. So to rewrite it in exponential form, I read this as 10 to the power of 1 over 2 to the power of 1/2 is equal to 2x minus 1. 10 to the power of 1/2 is equal to 2x minus 1. And we're pretty close to solving this problem. Once we've rewritten it in exponential form, we have a little bit of algebra left to complete. We need to isolate the term that the x is in. We'll do that by adding 1 to both sides. So we find that we have 10 to the power of 1/2 plus 1 is equal to 2x. And then finally, I'll divide both sides by 2. So we have x is equal to 10 to the 1/2 plus 1, all that divided by 2. So let's rewrite this as the square root of 10 plus 1 divided by 2. Since we're solving an equation, it's important that we remember that every time we take a square root, we have 2 answers. So we'll have plus or minus the square root of 10 plus 1, all divided by 2. So this gives us the square root of 10 plus 1 over 2, or negative square root 10 plus 1 divided by 2. So we find that x is equal to 2.08, or x is equal to negative 1.08. This is the first time that we've had 2 solutions, and we now need to check that both of these solutions are valid given the original problem. Remember that we can't take the logarithm of 0 or the logarithm of a negative number. If we substitute x is equal to 2.08 into the original equation, we're going to end up taking the logarithm of a positive value. But if I substitute in x is equal to negative 1.08 again into the original equation, we'll be taking the logarithm of a negative value. And this is not possible. As a result, x is equal to negative 1.08 is not a valid answer. And the only answer for the problem is x is equal to 2.08. Don't forget to check your answers in the original question every time that you solve a logarithmic problem. What about this next one? Well, here we have a sum of logarithms, both to the base 2, and that's equal to 3. So we can rewrite the sum of logarithms as the logarithm of a single quantity, where we'll multiply x and x plus 2. So this is the logarithm to the base 2 of x times x plus 2. And we find that equal to 3. Now I prefer to rewrite this in exponential form before I expand, because I'm going to take x and multiply it by x plus 2 using the distributive property. But the order in which you do these next steps is up to you. In any case, I'm going to rewrite this logarithmic expression in exponential form. So I'll take the base 2, raise it to the power of 3, and we'll find that that's equal to everything in the square brackets. In other words, 2 to the power of 3 is equal to x times x plus 2. We know how to solve equations, so let's get started. This gives us 8 is equal to x squared plus 2x. Since I have both an x squared and a 2x, I'm going to have to set the equation to 0 in order to solve, and I may have to use the quadratic formula because I have a quadratic equation. So I'll subtract 8 from both sides, so then I end up with a 0 on the left-hand side. So we find 0 equals x squared plus 2x minus 8. Now I find that I can factor the right-hand side. This is a quadratic trinomial that I can factor as x plus 4 times x minus 2. This means that either x plus 4 is equal to 0 and x is equal to negative 4, or x minus 2 could be equal to 0, giving a value for x of 2. Once again, I'm going to check my two solutions in the original equation. If I substitute x is equal to negative 4 into the original equation, I'll be trying to take the logarithm of a negative value, which is not possible. However, if I substitute an x is equal to 2, I don't run into this problem. So I find that x cannot be equal to negative 4, and x equals 2 is the only valid solution.